All right, let's go ahead and get started then. I just went ahead and shared my screen, so let me know if you can't see this. Okay, let me make sure that I can see our chat. All right, I got it up here, so we're good. All right, so last time, what we're really looking at was abstraction, okay? And what I tried to show you was kind of levels of abstraction, and what I'm going to say is increasing in this direction, okay? So at the very top, we had kind of physical components. And that might refer to things like resistors, wires, batteries. We also had a lamp, and we had a transistor. Okay, and all of these things are actual, honest-to-goodness physical components. I mean, I can pick them up, I can put them in some kind of a circuit. I can play with these. Okay, then underneath that, more abstraction, we can have models of the components. And I really didn't spend a lot of time in that, but just to show you kind of what I mean, an example of that is Ohm's law. Okay, and what it says.
Public Wi-Fi. You may need to update your connection. Take a look at the help section in your Alexa app.
All right, Alexa was just got excited when I said Ohm's law, apparently.
You may need to update your connection. Take a look at the help section in your Alexa app.
Okay, so Ohm's law relates the voltage that is dropped across a resistor, and it is equal to the current that flows through a resistor times their resistance in the resistor. Okay, V equals IR. If you don't know, what's the word I'm looking for? If you don't know the Ohm's law, don't worry about it. I mean, that's just a kind of a mathematical model of a real physical component, you know, a resistor that you would do in an electronics course or in a physics course, you know, electricity and magnetism, for example. Okay, so you're likely to see that in the future if you haven't seen it already. Okay, but that's a more abstract idea. And then on top of models of components, right, then we could actually do what's known as the digital abstraction. And the whole point of the digital abstraction was that we look, for example, at the voltage, and we said greater than or equal to 4, then we'll think of that as a 1. And if V is less than or equal to 1, then we'll think of that as a 0. Okay. And so if you remember in our circuit, we had things like voltages 4.48. That's just 1, and etc. And that's the reason, by the way, that I should say that the digital abstraction is so useful, because if you want to faithfully reproduce, say, a piece of music, and so you record it, right? Depending on the microphone and so on, you might get a voltage of 4.48 or 4.53 or, you know, something close to that, and so it's going to change. It's going to vary, right? The quality will vary over time, but not if you're doing digital, because whether you get 4.8 or 5.3, we know that that's really meant to be a 1, and so that's kind of the reason that the digital abstraction actually works, and that's the reason why, for example, we use digital DVDs or Blu-rays instead of analog equivalents. Okay, so it's a very, very nice abstraction. That actually led us to the concept of gates, right? And these are complicated circuits. But with simple, and that's the key, that's the power of abstraction, simple digital behavior, right? So I showed you what a NOT gate looks like as an actual circuit, and it's actually a pretty tricky circuit. But the concept of a NOT gate is very simple. If it's on the input, then the output is off. If the input is off, then the input is on. That's it. There's nothing more to that. Okay, and then for that, I kind of briefly mentioned the fact that there's memory inside a computer, and these are special circuits that remember a value, right? And often with a clock, okay? And what the clock is just a wire that goes on at a certain period of time. So when the clock goes on, then the memory looks at the input and goes, oh, I should turn to 3. And it just turns to whatever the input is, okay? I guess I should have said on or off if there's only 1 bit. There could be more than 1 bit. But if there's only 1 bit, then it would just remember on or off. And it'll remember whatever the input is when the clock fires, okay? So that's, we talked about these things last time. And we also talked about how to represent numbers, okay? And what we had here was several wires or memory components. Those memory components are called flip-flops, okay? And we interpret them in binary notation, okay? So for programming today, I'm actually asking you to write a program that converts numbers from decimal to binary and binary to decimal. And we're doing this all in terms of lists. So I wrote something very short that kind of tells you what I want there, okay? But right now, what I want to do is I want to continue this discussion. So now we know how to do numbers, okay? And the kind of a key idea is that numbers are n-bit numbers, okay? And n typically can be 8 or maybe 16 or maybe 32 or maybe 64, okay? All of these are powers of 2. And the reason that happens is simply because computer scientists like powers of 2. Powers of 2 come up naturally in binary, and so we just kind of start counting in powers of 2. That's not a fact. That's not a given. That's not something that should happen. For example, there were previous computers like the PDP, I believe the PDP-7, okay? There were several versions of that machine, but this one actually had 9-bit numbers, okay? So that's 9. 9 is not a power of 2, 8, 16, 32, those are powers of 2. So this is kind of an odd historical bird, right, if you will. But it's more common today to see this, right? But in any case, if I have 8 bits, then I can go up to 255, okay? 0 to 255, that's my range. If I have 16 bits, I go from 0 to 65,535, okay? 32 bits, roughly speaking, it's 0 to 4 billion, okay? That's 1,000 million. Okay. 64, that is absolutely huge, okay? So 1,000 million, this is 10 to the 9th, okay? So this is 4 times 10 to the 9th. By comparison, okay, this is going to be 16 times 10 to the 18 zeros. Those are gigantic numbers, okay? So we're usually in this range, right? As far as the computers are concerned. Okay, but anyway, that's what's going on with numbers. Okay, now how do we represent other things, like for example letters? Okay, and when we were trying to do this historically, okay, so when we were doing this historically, we were dealing with very small computers. Okay, and in particular, very small memories. So one of the obsessions of those of us in computers back then was how to make, just squeeze everything out of every single bit, okay? So what they did was they said, okay, so we have 26 letters, okay, times 2, so that we have upper and lower. Although back then, that was considered a luxury, right? I mean, you were perfectly happy to live with just uppercase letters, all right? But let's say that we have that, so we actually have 52. Then we have a few punctuation marks, okay? And punctuation, what am I talking about here? Space, comma, the dash, colon, semicolon, period, exclamation mark. I don't know, let's say 10 of those, okay? I mean, just kind of a round number. Maybe I need 15, right? But anyway, right here, there's 62, okay? Oh my God, I need numbers, okay? So I need 0 through 9, okay? So that's 10 more, so now it's 72, okay? That's actually kind of a sad moment because 64 is 6 bits, okay? 72, I now need 7 bits, okay? And people just kind of started saying, well, what else could I need? Quotes, double quotes, maybe 10 is a little low, but still 72 is going to grow to like 82 maybe, definitely not too much bigger, okay? So 7 bits is really all that we need, okay? And then people started thinking, well, it might actually be useful, okay, to have some extra characters. And so those characters, for example, are like Control A, Control B, and so on, right? And so in here, I'm basically doubling the number of characters that I have, okay? Now, people actually gave some of these special meanings, like Control I is a tab. Why? Because somebody said so. Control J is a new line. Again, why did we pick Control J? You have to pick something. And it was a character that was invisible, and so the tradition became that these were invisible. Okay. So that's how we ended up building a scheme. And somebody wrote it down, and we ended up building what's known as ASCII. This is something like the American Standard for Computer Information Interchange, or something, code, I believe, not computer. So that's not important. It's just a convention. I want to say that it wasn't even the first one. The first one was something called EPSTIC. Okay, so this came first, and then it disappeared. This came second, and this is the one that stuck. Okay, so it's kind of the popular vote. But all it is just a convention. So I have in front of me, otherwise I wouldn't know this, okay? But I have in front of me some entries in the letters. And so, for example, I see that a space is actually the number 32, okay? And for example, an exclamation mark is the number 33, okay? The number 0, okay? Remember, this is actually a quote letter, right? So 0 is actually 48. 1 is actually 49, okay? And so on. And then we have things like lowercase letters. So for example, a lowercase a is 54, I think. Nope, not even close. 97, okay? And I should have put capital A first. Capital A is actually 65, okay? And lowercase a is 97. So one lowercase z, for example, happens to be 122. And there's no particular reason why it should be that, okay? But this is just a convention. Now, some people actually memorize some of these. I don't, okay? It is useful to remember that by and large, punctuation comes first. And then we have digits. and then we have the uppercase, and then we have the lowercase letters. Okay. The only reason I say that it's useful to remember that, for example, in a computer, exclamation mark cat happens before cat. Okay. Capital cat happens before lowercase cat. Okay. And the number 3 cat, for example, happens before all of those, right? So that's why it's semi-useful to remember that. But other than that, it's not worth the detail. Now, in the AP exam, they might actually ask you, some of this stuff, but they'll always give you a table, okay? So you just look it up in the table. And the kinds of questions that they'll ask might be something like, what has more ones in the ASCII code? A or B. So you look up the number, you convert it to binary, and count the number of ones.
Oh, wait, I don't
A has so many, B has so many. So clearly it's, actually I believe they're going to be the same, but it doesn't matter, right? That's the kind of question that they might ask. Okay. But anyway, that's how we do letters. I want to tell you something that is depressing, right? This distressingly sad. And that is that nobody thought about other languages. And by other languages, I'm talking about things like Spanish, German, French, Arabic, many, many dialects of other things like Chinese, okay? Russian, etc. Okay, I mean, there's a lot of languages, and for some reason, when people started, sat down to come up with this code for representing letters, they simply didn't think about any of those. So, for example, in Spanish, you have an ñ, right, which is an N with a little thing on top. We also have accented letters like E. Okay, in German, we have some really weird letters like a long shape like that happens to be the same as a double S. They also have other letters with different kind of adornments. French, you might have a C with a dia. You might also have other vowels that have different kinds of accents. Okay, I won't even go into Arabic or Chinese or Russian, although Russian again has different alphabet. Greek has a different alphabet. The point is, we simply didn't make any room for this, and they were completely and totally left out. And by totally, what I'm saying is this: we have 8 bits, right? That means that there are 256 different possible letters, and that's not enough. Like some of the Chinese alphabet, for example, can have thousands of quote letters. There is what's called the simplified alphabet that doesn't quite have as many, but that was just unfortunate. Yeah, good for you sending me some different letters. Okay, so as you can tell, right? Some of this stuff, in fact, all of this stuff was done originally in English-speaking countries, and then we started trying to move computers and make them available to other people, and God help us, right? So we couldn't. We had some problems. Okay, so what we had to do was we had a choice. We could abandon ASCII, okay, or we could expand ASCII. Okay, and what we chose was number 2. Okay, we wanted to expand ASCII for a very simple reason. All the computers already knew about ASCII, right? So rather than completely start from scratch, we decided to expand it. Okay, now that leads to kind of a funny kind of situation. If you have a number in the range 0 to 255, right, then it is like the old ASCII interpretation. Higher than that, then is what is, well, I'll just jump right into the current state of the world, and it's what we call Unicode, okay? So this can lead to some kind of weird things because you have a letter E, right? And then you might have an E with a tilde and an E with a back tilde. And this is definitely less than those because this will be greater than or equal to 256, and this is less than 256. Okay, so this is the ASCII letters. They're old and they don't change, and these are the Unicode letters, which are new and can actually encode all these different things. So yeah, that's tricky, right? So somehow we have to be able to represent those. That's what Unicode is kind of clever about. Okay, and depending on where you are, and this is what's known, and this is a technical term, your locale. Okay, then you end up with different alphabet, and very important, a different sort order. Okay, that's what I'm trying to get at here is this sort order. Okay, because we have to agree on the way to alphabetize names, for example, right? And God helps us, Canadian French alphabetizes differently than French, which I hate to tell you is different than Belgian French, and so on. Okay, and the differences can be that one word is alphabetized differently depending on which language you claim to be. So is it early in the does it come before the lower cases, after the lower cases, in between? All of that is defined by this. Okay, the different sort order. So I saw you guys asking the question, how do you change your keyboard? Go to settings and look under locale, and it's as simple as that. I have many students, for example, that routinely come to me with computers that are in a Chinese locale, and then I can't use the computer at all, right? But they're just fine. So that's a good thing, right? You know, but finally, yeah, American English and English, which the spelling is different, so that changes the spell check and also a few other things like that. So yeah, that's the way it is. This one is especially painful because, for example, does U double dot, is that before U or is U before U double dot, right? That depends on what dialect of German you're using, for example. It's like, oh God, stop, right? We don't want that. But we're humans. Different places have different conventions, and computers respect that now, right? Because of Unicode, right? Expanding ASCII, that is Unicode. Okay, so that was really a nice thing. Okay, so that's how we do letters. Okay, what else can we store in computers? We can store, for example, colors, and we talked a little bit about that earlier and last lecture, but let me review some things. Chances are that your computer is a 32-bit computer. It might be a 64-bit computer, but even with those, we still do a lot of work in just 32 bits. And when we have 32 bits, we break them into 4 quote bytes. And each one of those then will be 8 bits. Okay. Even in a 64-bit machine, this is very likely to be colors. So with colors, basically what we do is we store the intensity of the color. And that is some kind of a number from 0 to, I'll just call it max, okay? And max, some work was done early on. So for example, we had some kind of psychological studies to see if you see a picture that has all red in it, can you tell the difference in the shades of red from here to there? And it turns out that 255 different, 266 different colors going from 0 to 255, that is about as good as you need, okay? Your eye can't detect much more than that anyway. So 0 to 255 is actually reasonable to store intensity. If you really cared about lowering the number of different colors, right? Or, so that you save memory, then you might only have 8-bit colors. Games in the 1980s were in 8-bit color. And so they have very vibrant colors because there's no subtlety, right? Because you don't have that many colors to choose from. So anyway, so that's why that was done. Now we can actually give 32-bit colors. Might as well do 32 bits because computers, you actually have lots of memory now, so you're not worried about making it small, and they naturally do 32-bit words. So that's why we choose 32. And what we need now is to store the different intensities. Now, one secret is that we see 3 different colors. That's actually all we see. And that's because we have cells that are sensitive to those specific colors, okay? If you're colorblind, then I hate to say that you don't actually see all 3 different colors. So that's something you have to be sensitive for. And that's one of the reasons, for example, that when you're designing a web page or a user interface, then you want to choose colors that have high contrast, right? Light versus dark, because that's something that everybody can see, okay? Anyway, since we see the 3 colors, then what we did is we designed computers to kind of give you those 3 different colors, and they're red, green, and blue, okay? Those are the 3 colors that we can identify. Each one of those, 0 to 255, that is actually 8 bits. So that's perfect. Red, green, and blue, each one of them has 8 bits, okay? The way that we'll store those, it doesn't matter, right? It's just 8 bits. But the way that we tend to speak to each other about them is by using hex digits. Why hex? Because if I have 8 bits, then I can simply memorize that is a D, okay? And that is a 9. So it's pretty easy to actually describe colors in using hex, just because we learned those 16-inch digits in hex, okay? It's certainly easier than typing, 8 zeros and ones, okay? So we might say that this is D9, 25, 1A, right? And this is a color that's going to be predominantly red. It'll have a little bit of shading in green as well as in blue, okay? Pure red would be FF. FF is 255. That's the biggest possible intensity of red. And then 0 for green, 0 for blue. Likewise, pure blue would be 00 FF, right? So that's so those are some kinds of colors. Okay. Okay. Now, this is fine. And actually in HTML, you can say, this is just a HTML convention. So for web pages, hatch FF0000, and that is just red. Okay. Now, in more advanced programs, like for example in Photoshop or the GIMP or something like that, they take care of this. And what they do in here is something called alpha. Okay. And here's the idea. Let's say that I have a red, well, that's supposed to look like a rectangle, so humor me. This is supposed to look like a circle, okay? And let's say that this is red and this is green. So if the circle is in front of the rectangle, then of course it's going to cover it, okay? But what you might want is exactly the alpha channel is something that clears it up. So the big question is, how opaque is this circle? Okay. If it's completely opaque, right, then all I can see is the circle. I can't see anything underneath it, right? But it's actually partially transparent, right? Then I can see through the green and detect some of that red coloring of the rectangle underneath, okay? So that's what alpha is. So if we have something like 00 to FF, 00 is completely opaque. FF is, I believe, completely transparent. I may have those mixed up. I'm going to look it up real fast. Thank God for Google. It is going to be the okay. So one is in fact completely completely opaque. So this is totally opaque, and this is totally transparent. Okay. In any case, it doesn't really really matter. The when you're using something like Photoshop, right? And you simply put in the thing, you got a little slider that you move and say, how opaque do I want it to be? Okay. So that's what that's used for. Okay. That's not really a color, right? That's just simply how do I display this? And more sophisticated programs will actually do more sophisticated things. For example, you might have something that's like a mirror and that reflects and all those kinds of issues. We don't catch those. The only thing that we match is what percentage of opaqueness do we have, and percentage in terms of 0 to 1 over to 1 in steps of 1 over 256. Okay. All right. So that's the story for colors, right? So summary in colors is that we have the alpha channel, we have the red, green, and blue, and this is a 32-bit word. Okay, so let's move up. Okay, and again, going in increasing abstraction, now we can have a picture. Okay, if you look on the web, you're going to find pictures of that are going to be basically rectangles, okay? And you have a number of rows and a number of columns, okay? We usually describe the horizontal component first. So this is the number of columns, this is the number of rows, right, going down, and we say cols times rows, picture, okay? Let me check what my system has. This is my computer, and it listed as 2560 times 1440 resolution, right? That's my monitor. So that is the number of columns that it can display, and that is the number of rows that it can display. So as you can see, it's wider than it is tall, all right, which is pretty typical for monitors these days. Okay, so that's how we kind of say the shape, the size of a picture. Okay. Now each one of these, then we have here a specific row, right, and a specific column. And what we have here in the middle is a pixel. And what is a pixel? It's just a color. So it's alpha, red, green, blue. Okay. I'm going to just say quote end of story. Okay. Not entirely, okay? So if you end up with this, like for example, if I had a picture that's 1,000 by 1,000, that would end up being 4 million pixels. And because I have this 32 bits, it would end up being 16 million bytes. That's what we call 16 megs. Okay, 16 megs for a single picture, that's a lot, okay? And you simply don't want to, store that much. I mean, eventually you run out of memory. So we tend to take advantage of two big tricks. Trick number one, suppose we have relatively few colors. Then what we'll do is we'll say color one is equal to some red, green, blue combination. Color 2 is equal to some red, green, blue combination. Up to, say, color 78 is some red, green, blue combination. And then we'll describe an array. Okay, this is the rows. This is the columns. And now each one of those pixels is just 8 bits. Okay. I could even get away with 7 bits, but I'm not going to be greedy, okay? I'm going to stick with 8. And notice that that is enough to refer to which color I'm describing. I don't have to give the whole color each time. I'm simply telling you, oh, it's the third color that I use in this picture, and the third color happens to be purple, okay? So that's this idea, okay? This is known as a color map, okay? And I'm just gonna beat a dead horse. I mean, I realize that the horse is dying, but I want it to die. This is an abstraction, okay? Right? Because now I refer to color number 12, right? Instead of actual red, green, blue components, it's just color number 12. And now my file, okay? So this is the way that I represent an image. I have a header, which has the color map. Okay, these are the colors that I will use. And then I will simply have an entry for each pixel. Okay, so this is one way of encoding the colors. Okay, here's another trick that we use. So this is trick number 2. Okay, if you look at a scene, okay, so we're going to find out that I'm just a fantastic artist here. Okay, so here is a person, right? And is a very happy person. And there is the background. So what might happen is that, for example, they're standing in front of a wall. So all of these are just white. Okay, and then it gets more complicated, right? But then all of these are also white. Okay. So absolutely. I mean, I need brownie points for my artwork. Okay. Now, because those are all white, then I can actually give a description that says something like this: 38 pixels of just white, followed by 1 pixel of some RGB, and so on, and then 157 pixels of white. Okay. So that's actually how I describe this image, and this is called run length encoding. Okay, and the basic premise behind run length encoding is that if instead of giving you white, I can simply say X whites, right? And that's going to be a smaller description than I would need otherwise. Okay, these tricks can actually compress a file quite a bit, image files, especially when there's a lot of colors that are the same, right? Now, trick number 3 is math, okay? And with trick number 3, what we basically want to do, right, is just use fancy math, okay? I'm thinking in particular of things like linear algebra. I'm thinking in particular of things like coding theory, okay? And I'm just going to give you the names and that's it. I'm not going to tell you more about it. I'm simply going to tell you that the whole point is that we use these kinds of ideas. There's probability here too. We use the fancy math to basically take a big file and convert it into a small file, okay? And this is called compression. Okay. And you can think of the compression as a function, right? So f of this big file is equal to that little file. I mean, that's really what it is. And then there has to be some kind of a inverse function. F of little file is equal to the big file, okay? And as long as you know f and f inverse, then you can simply run that on your file, create a smaller file, and then do it inversely. This can be specialized for images or not, okay? So you can use general compression techniques that just work for a lot of things, or you can use something that only works for images, okay? Only thing I'm going to tell you about compression besides what I already said is this. F and F inverse maybe approximations. So for example, let's say that I have a big file and there is a tiny dot in the middle, okay? That is black. Everything else is white, okay? So one compression could just simply be all white, okay? If you do that, right, then it's really a great compression, right? I mean, it's just a tiny description of the file, but you end up building something that's not exactly what you started with, right? Or you could actually say all white except, right? And so this one recreates the image exactly. This one approximates image. Gives you better compression. What does that mean? It means that I end up with a file that's smaller. And this one, you know, it's just okay compression, right? It's not as good as it could be. So how badly do you care that you get back the original image, right? That's the question, and it's entirely up to your usage. So what we have is what is known as lossy compression, and then we have lossless compression, right? So think about it as a spectrum, right? So we have lossy compression here, better compression, meaning smaller files. And then we have lossless compression, which is worse compression. And what does that mean? It means that you have bigger image files, right? So you get to choose what you want. I know, for example, professional photographers pick a little button that says, don't even bother compressing, right? I'm gonna do I mean, I wanna know every pixel exactly as I got it, and then we'll deal with it. They call that raw images, okay? Whereas, for example, for me, since I'm not a high quality photographer, compress because I just wanna have small files. Okay, that's images, okay? So let me briefly talk about video, okay? In video, I have an image file, and then another image file, and then another image file up to that, okay? So this is an image, another image, another image, okay? And essentially, I'll do the same thing that, that we did before, right? I can compress each image independently. Now let's do a very, very quick sanity check, okay? So I want something on the order of 30 images per second for video. This is also the frame rate, FPS, frames per second, okay? And 30, right? So 30 per second. Let's see, how much, I'm saying movie images, but let's say it's an hour long. So 60 times 60, okay? So this is hours. I'm sorry, this is minutes. That is seconds. So that ends up being 1 hour, okay? And how big is each file? I'm gonna say 1,000,000. I mean, not file, each image, okay? This is 1,000 by 1,000, which is reasonable quality for like television. Not as bad as the really bad quality television, but not nearly as good as a you know, high quality movie, high definition movie. So I could actually just do this in my head, but I'm not going to. So I want to make sure that I nail it, okay? $24 is the minimum that you can use. More than that, your eyes will actually realize that, that some compression is happening. Okay, so the size of this is 1.08 times 10 to the 11th, right? And so that ends up being 1.08 times 10 squared times 10 to the ninth. This is a gig, okay? That is 1,000 million, okay? This is just 108. So we have 108 gigs, except I made a mistake because I need the alpha RGB, right? So I'm actually going to need to multiply that by 4. So 432 gigs. Okay, that's a big file. Okay, it's actually, that starts being ridiculous. So we may not want to use this format. Okay, so that's why we have video compression. And what kind of ideas can we use? We can use all of the tricks from just images. And then we can also look at over time. So you guys liked my picture, so now I'm going to show you a different picture. This is an action, okay? So here's my hero. Notice that angle because, he is doing something cool. He has a ball that he's throwing. And then the next frame, here is my hero. He is at that same angle because he just finished throwing the ball, which is now over here, okay? So as you can tell, if I pick a pixel, it's probably the same, right? This is the only thing that changed. So when we're doing that run length encoding, okay, when you're doing that run length encoding, not only can you encode within an image, but you can also encode over time, okay? So you could just say, this is the same as the last one, right? And that significantly reduces the amount of data you need to store, okay? So we need a specialized video compression. There's lots of competing formats. And eventually it becomes less about computing and more about politics and business. Who actually controls the format? Okay, so that's unfortunate, but that's part of computing. Okay, as always, there is a trade-off. You can have better resolution, right? Better quality, higher video quality versus size of the data. And it's not just the size of the data that you store; it's also the time that it takes to transmit over the network. So for example, if you're trying to watch videos on your phone, right, it takes some time to get the data going. So that's that, okay? I want to end this kind of by talking about audio, okay? Do realize that when we're talking about audio and when we're talking about video, video actually typically comes in multiple channels. One of the channels will do audio, so you can actually, they're not, silent movies anymore, right? So what do we do with audio? And what we have there is actually relatively easy. What we mean is that when somebody's speaking, right, they actually generate some kind of an audio wave, okay? And this is quite literally a sound wave, okay? And then we put a microphone here. And that converts it. This goes through a wire, and what we have is an actual audio wave. Okay, so how does that work? Well, this is, basically the way that any microphone works. We have some kind of a surface, and then we have sound waves that are going through it, and the sound waves then will make this a membrane, okay, move back and forth, okay, oscillate as the sound, which is actually just compressions in the air hitting it, right? So it'll go up and down, and then we'll measure the compressions. So how compressed is it at this time? Okay, and the answer to that actually has a name. It's called the amplitude. Okay, and we simply record that. So this might be a number between, say, minus 500 to 500, okay? Just say to positive 500, okay? So you know, and you can actually choose different levels of that, right? That tends to be what we refer to as 8-bit sound, 16-bit sound, and so on, okay? All right, so that's the amplitude. And then we'll measure this every 1 blanks, okay, of a second. The first people who really cared about this were the phone company, right? Because the phone company had to, you know, you're talking on the phone. How often do I measure what your voice is doing, transmit that over a wire, and reproduce that movement over on the other side? And the phone company needed that to be reliable so that people could speak and be understood at the other end. And they didn't want to take as many bits as possible, right? They wanted to take as few bits as possible so that they could transmit it over a large distances, etc. And so they chose, after many experiments, kind of a standard frequency of 14,000, roughly speaking, somewhere between 14 and 15,000 times per second that you try to listen to this. So that's the frequency that we use. Even today, that's usually the default frequency. If you do like a video or an audio recording, like for example, I bet I'm being sampled right now at roughly that rate, you know, 14,440. But you can adapt that, right? You want higher quality, then you'll measure the compressions closer together, and that means that you end up with a larger audio file, right? Like anything else, this just ends up being a file of numbers, right? In Windows, for example, there are files that have the .wav format. They are literally that, just that this, you know, just a sequence of numbers one after the other telling you what the different amplitudes are. As with everything else, that ends up being a very large file, so you can run it through some kind of compression, and there's different compression mechanisms, right, that you can use. So that's how you get this multitude of audio file formats. There's just different ways of compressing the data. That's all there is to that, okay? And that's it, okay? That's how we store audio. Like I said, video files actually have an underlying audio component or track. You can have several audio components or tracks. For example, if you want to do stereo, or if you want to do, you know, 5.1 Dolby, or, you know, 11 whatever, you know, all the way down to IMAX surround sound. So that's just lots more channels. Okay, so the goal of all this was simply to show you the way that we store data in computers. And I want you to get a feel for that. Just especially, I want you to understand the trade-offs. You know, higher quality versus smaller file sizes, faster time to send over a network. Okay, so Netflix cares deeply about this, right? You know, how do I keep my customers happy without killing the internet in the process? Okay, and as more things come up, like for example, GIS maps, okay, then or Word files, or, you know, Excel files, and so on. I hope you appreciate that all it is a choice of format, and so we have a whole bunch of data to store, and we simply choose different conventions for how to do it. Like, oh, a picture is just a two-dimensional array of colors. Awesome. Okay. All right. I'm going to go ahead and leave that, and I want you to kind of take the rest of the time and try to write those blocks that I was describing, which will convert a decimal to binary and binary to decimal. And I'll just say a few things so that you remember. Going on decimal to binary, you might start with a number like 23, and then the question is going to be odd or even. Okay, and if it's odd, then you'll put a 1. If it's even, you'll put a 0, and then you'll divide by 2 going down. Okay, so 23 divided by 2 is going to be 12, because we get rid of the remainder. That is even. Again, we'll divide by 2, 6. That is also even. Divide by 2, 3. That is odd, so we put a 1. Divide by 2, we'll get 2. Okay. I'm sorry, what am I doing? You'll get a 1 because we're rounding down. And so Did I get this right? Hang on, 23 divided by 2 should have been 11. Oh, I have to start over. Bummer. Let me use the eraser here. See, that's why we write programs to do these things. Okay, so we're always taking just well, we're always rounding down. We take the quotient and throw out the remainder. So when I divide this by 2, I'm going to get 11 with a remainder of 1. So we put the 1 there, 11. That is now odd, so I keep that. Divided, I get 5. That is still odd. I keep that. Divided, I get 2. Right? Divided again, I get 1. Move the 1, and that's it. And then I write the number in this form, 10111. Okay. What you'll want to do is use lists. Okay. So that you end up with the list 10111. Okay. This is actually a block that's in Snap. I do want to tell you kind of a trick. Okay. Write a block. There is already a block that says something in front of a list. And what it does is it returns a new list where we take this number and put it here, and then take these numbers and just copy them over there. Okay. So for example, 3 in front of the list 2, 4, 6 is equal to the list 3, 2, 4, 6. Okay. So write a block called something at end of a list. So if this is 2, I'll make it 3, and this is 2, 4, 6, then the result is going to be 2, 4, 6, 3. Okay. The reason I suggest you do that is because you see we find this one first, but this one actually goes at the end. Okay. So that's if you write that block first, it will simplify your task. Okay. And for binary to decimal, okay, then what we'll do is you can start with this, and then it becomes I think it's better to just start at the end. You can do it either way, but I think this is the way I did it last time. So this becomes 0 plus 2 times, and then whatever that converts into, okay? And that is 1 plus 2 times, and then whatever that converts into, which is 0 plus 2 times whatever this converts to, which is 0 plus 2 times whatever that converts to, which is a 1. And if you unravel that whole thing, that will actually be the decimal representation. So you might go ahead and use that instead. Okay. So anyway, go ahead and give those 2 programs a shot. If you have questions, let me know. All right, I'm going to stop the recording so that we don't grab everyone else.